Good afternoon, everyone. My name is Jakob Hinney. I'm a postdoc at Columbia University in the group of Lipson. And today I'm going to report on the loading of short pulses into long lifetime cavities. A common situation that you encounter in photonics is one of a pulse, potentially very short, characterized by a lifetime or a pulse time, interacting with a cavity that is characterized by a certain frequency profile. And the relation between pulse duration and frequency profile of the cavity determines the strength of this interaction between pulse and cavity. And you can have the situation that if this interaction is very weak, the pulse basically transmits the cavity with very little modulation. And the stronger this interaction is, the more of the pulse will be loaded into the cavity and the output of on your bus will be more extinguished. So to put it a bit more concrete, we have a ring resonator, we have a bus that couples to it, we have an input pulse that in the and we have transmission. And in our experiment, how this looks is we load Gaussian pulses, duration of a few nanoseconds, in this case 4 nanoseconds, full width half max, and they transmit this cavity that has a Q of a few million, and that corresponds to a lifetime of also about 4 nanoseconds. And then we can record what comes out of the on the bus, and from this infer also how we loaded the cavity. And then one way to visualize such a one data point is just to plot them together, and you can already from the ratio between the orange area output and the blue area input, you can get an idea of the efficiency of this loading. And I should say that we always do this on resonance of the cavity. And what I'm going to show you today is that in such a scenario where you look at the loading of your pulse into the cavity, you can obtain a stronger or a better loading efficiency if you in fact supply your pulse with a CW offset, which amounts to basically modulating your pulse less, and you get more loading from it. And that's what I'm going to present to you now. The experimental setup is very straightforward. We modulate the pulses using NEOM, send them to a silicon nitride chip, this 150 micron radius, I believe, and has a few million Q, again, about 4 nanosecond lifetime. And then because we are dealing with very short pulses, we have to amplify them and we can detect them. And to quantify this process, again, here's the setup. We coin this efficiency for which we integrate the area under our pulse, the output pulse, and normalize it with respect to the input pulse, subtract from 1. So we have an efficiency that is high if we have a lot of pulse loaded into the cavity, and vice versa. If the pulse transmits more or less unchanged, it's very low. And so in the first scenario, we just look at the passive resonator, just input field and input pulse, and then we look at this loading efficiency. And in this plot on the x-axis here, that's the offset that you see here, and the loading efficiency as you increase that offset. And we can take a look at the pulses, the underlying sort of data points, what that actually means. So you see initially no offset, and then the offset goes up, and the efficiency at which you load the pulse into the cavity also goes up. Okay, so that's already something, but now we want to see what happens if our cavity becomes better, that is, it becomes lower in loss, and therefore more narrow. And there's a way in which we can achieve this in this on the same chip by adding a pump field that is co-propagating to the pulses. And yes, and this pump field is detuned a few nanometers from our probe resonance. That will be over here, and the pump is here, a few milliwatts, on the order of 10 milliwatts maybe. And then that leads to a gain profile extending around the pump resonance. And that affects the resonance at which we load the pulses. So in the passive scenario, the resonance looks like this, has a few tens of megahertz line width. And then as you tune your pump into resonance, you get gain. That means you reduce the losses in the resonator. Your resonance narrows significantly, and now corresponds to something of a lifetime on the order of 50 nanoseconds. So now your resonator has become a lot longer in lifetime, long-lived. Okay, so now let's look what this does for the efficiency of our pulse loading. So here we see the data that I showed you just before in the passive scenario. Now in the high Q scenario, you see that the same effect actually is a lot more pronounced. And if we look at the underlying pulses, what that means, here for the low offset, more or less the same. But then you see that as we increase the offset, this pulse disappears almost completely. And so it is loaded at a much higher efficiency. And so how can we make sense of this? What's behind this? The way we like to think of it is that your Gaussian pulse normally comes with a frequency profile that is also Gaussian. And now this frequency profile, again, has to be compared to the cavity frequency profile. And what we do by adding this offset to the pulse is that we end up with a sort of DC peak at the DC frequency in the frequency profile. And now this means that the pulse frequency profile matches that of the cavity better. And if the cavity becomes more narrow, in our case, because of the gain, that effect becomes even more beneficial. And this ends up having the effect that modulating our pulse less ends up to a higher loading of the pulse into the cavity. And that's what I wanted to tell you today. We can enhance the loading of our pulses into the cavity by supplying them with a CW offset. And this effect becomes even more pronounced as your cavity becomes more narrow. Okay, and that concludes my content. I would like to also point your attention to other talks from our group, from the Lipson group. These were already today, but you can see them online, and the authors are here at the conference. And on Friday, then we have one more talk coming up. And I'd like to thank my coworkers in the Lipson group at Columbia, and I'm happy to take any questions